Somewhere south of Grantham, in the summer of 1938, a fireman in a shaking steel cab caught a smell that did not belong there. Not coal, not hot oil, not steam. Aniseed, sweet, sharp, unmistakable, like a sweet shop had been dropped into a furnace. He knew exactly what it meant. Under the boiler, between the frames, buried in a place no man could reach while the engine was moving, a small glass capsule had just burst. It had been put there deliberately. It was a warning device. And it only broke when a bearing deep inside the locomotive got hot enough to start destroying itself. At that moment, the machine he was standing on was traveling faster than any steam locomotive had ever traveled in human history. It was still accelerating. The record it set that afternoon has never been beaten. Not in 88 years. Not by anyone. And here is the part that almost nobody mentions when they talk about it. The locomotive did not roll triumphantly into London. It never finished the journey. It was quietly uncoupled at a station along the way, replaced by an older, slower engine, and towed off to a workshop with molten metal running out of its bearing. So this is the question worth asking. Not how fast can a steam locomotive go, but what actually breaks when it gets there. Why is there a wall in front of these machines that no amount of money, coal, or engineering brilliance has ever pushed through? To understand that, you have to stop looking at the outside of the locomotive and start thinking about what is happening inside it 60 times every second. Because a steam locomotive is not like an electric motor or a jet turbine. It does not spin smoothly. It punches. Think about what is really going on down at wheel level. In each cylinder, a heavy steel piston is being driven forward by steam pressure. It reaches the end of its stroke, stops dead, and is driven back the other way. Stops again. Reverses again. That piston, along with the connecting rod bolted to it, weighs several hundred pounds. And every single time the driving wheels complete one revolution, that entire mass has to be brought to a halt and thrown in the opposite direction. Twice. At a gentle 30 miles per hour, that is a manageable thing. At 120 miles per hour, those wheels are turning roughly 6 or 7 times a second, and the forces required to reverse all that steel are enormous. Not hundreds of pounds. Tons. Tons of force, applied and released, hammering through the crank pins, the bearings, the axles, and the frames. Engineers had a word for what this does to the world outside the locomotive. They called it hammer blow. It is the reason a fast steam engine does not merely run on the rail. It beats on it. Every rotation drives a pulse of force down through the wheels into the track structure below, and at record speeds, the track itself can be pounded, shifted, and left needing repair after a single passage. Now flip that around. If those forces are strong enough to damage the ground, imagine what they are doing to the machine generating them. This is the central paradox of high-speed steam. The faster you go, the harder the engine attacks itself. Not gradually, not linearly. The forces climb with the square of the speed, which means every extra 10 miles an hour costs far more than the last 10 did. A locomotive at 120 is not doing twice the internal violence of one at 60. It is doing something closer to 4 times as much, in a mechanism made of cast steel, white metal, and bolts, lubricated by oil, that is being flung outward by the very rotation it is meant to protect. Which raises an obvious question. If everybody understood this, Why on earth would anyone deliberately push a steam locomotive to the edge of destroying itself? The answer has almost nothing to do with engineering and almost everything to do with pride. The 1930s were the last great decade of the steam railway, and the men who ran them knew it. Airplanes were getting faster, roads were spreading. The railways, which had been the fastest thing on the planet for a century, suddenly had rivals, and they responded the way industries always respond when they sense the ground moving. They turned speed into theater. Streamlined locomotives began appearing across Europe and North America, wrapped in smooth metal shells that made them look less like machinery and more like something launched rather than built. The casings did real aerodynamic work at high speed, but they were also advertising. They were designed to be photographed. Railways painted them in colors that had never existed in the industry before, gave them names, put them on posters, and sent them out to break each other's records. In 1936, a German streamliner reached just over 124 miles per hour, and the British took that personally. The British answer was a class of streamlined express engines designed by an engineer named Nigel Gresley, and one of them, 4 months old, freshly painted, and barely broken in, was about to be handed the hardest job any steam locomotive has ever been asked to do. Here is what mattered about that machine. It had 3 cylinders instead of the usual 2. 2 of them sat outside the frames where you could see them. The third was hidden between the frames, driving a cranked axle. 3 cylinders meant more evenly spaced power impulses, smoother running at speed, and less of that brutal hammer blow on the rails, which is precisely why the design was chosen for high-speed work in the first place. But the third cylinder came with a complication. A cylinder needs a valve to admit and cut off steam, and a valve needs its own gear to drive it. Fitting a third complete set of valve gear in the cramped, filthy, inaccessible space between the frames was a maintenance nightmare. So Gresley used an elegant shortcut. Instead of giving the middle cylinder its own gear, he drove its valve from the motion of the outer 2 cylinders, using a system of levers that mathematically combined their movements. On paper, it is beautiful. Fewer parts, less to maintain. In practice, those levers had pins, and pins wear. And as they wore, the middle cylinder's timing drifted. It began taking a longer bite of steam than it should have, doing more work than it was designed for, while the outer 2 quietly did less. At normal running speeds, nobody cared. At 120 miles an hour, that inner cylinder was hammering a bearing that was already the hardest bearing on the locomotive to inspect, to lubricate, and to reach. The engineers knew. That is the detail that changes the whole story. They already knew that middle bearing was the weak point because it had been running hot on these engines before. And rather than solve it, they did something almost absurdly pragmatic. They installed a warning system. A little capsule of aniseed oil tucked into the bearing itself that would burst and fill the cab with the smell of licorice if the metal began to overheat. They did not build a bearing that could not fail. They built a bearing that would tell you when it was failing. Which brings us back to a hot afternoon in July and a driver named Joseph Duddington and the last, best, and only serious attempt his railway would ever make. The official reason for the run was a brake trial. Everyone involved understood that the real reason was the record. The train was short by express standards, a handful of coaches plus a special carriage packed with recording instruments, its stylus scratching speed and distance onto a moving paper roll. It would be the only evidence that mattered. The route was chosen with care, not a level track. A long, gentle descent, a place where gravity would quietly join the crew as a third member of the team. They dragged the train up the climb, over the summit at a modest 75, and then the driver opened the regulator and let the machine have its head. What happened next was recorded mile by mile, and the numbers read like a countdown in reverse. 87, 96, 104, 107, 111, 116, 119. Then the intervals got shorter and the readings kept climbing past 120, 122, 124, until for one moment the stylus scratched out a number no steam engine has ever equaled since: 126 miles an hour. In the coaches behind, this was not a serene experience. The train rocked so violently that accounts describe crockery smashing in the dining car. Red-hot cinders were flung from the chimney with such force that residents of a village along the line reported windows broken by them. This was not a machine gliding. This was a machine being flogged, and everyone on board knew it. And in the cab, the crew smelled aniseed. It is worth pausing on what those two men were actually doing. A steam locomotive cab at that speed is not a cockpit. There is no seatbelt, no windscreen worth the name, no instrument that tells you what the machinery beneath your boots is doing. The floor plates are moving relative to each other because the locomotive and its tender are separate vehicles hinged together. The noise is beyond conversation. The fireman is swinging a shovel into a firebox door while the whole world lurches, feeding a fire that is consuming coal faster than any man can comfortably supply it. And the driver has one hand on a regulator and a set of instincts built over decades, and nothing else. They were not flying a machine. They were riding one. The instruments that recorded the record were in a carriage behind them, not in front of them. The crew learned how fast they had gone the same way everyone else did, afterward, from a piece of paper. What they did know, in the moment, was the smell. If you are enjoying this, take a second and subscribe. We dig into locomotive history and railway engineering every week, and there is a lot more where this came from. The moment the speed peaked, the run had to end. There were junctions ahead with speed restrictions, which meant the brakes came on hard, and the sudden change of load through a mechanism that was already at its structural limit was the final insult. The bearing on the middle connecting rod had been getting hotter for miles. Now it gave up entirely. Inside that bearing sits a soft metal lining, a low melting point alloy poured against the steel. Its whole purpose is to be the sacrificial layer, the surface that carries the load and holds the oil film. It is designed to be softer than everything around it, so that if something goes badly wrong, the cheap replaceable part fails instead of the crank axle. That is exactly what happened. Not an explosion, not shrapnel. Something quieter and, in its way, far more revealing. The bearing metal melted. The locomotive that had just outrun every steam engine in history had, in the process, liquefied a part of itself. The crew nursed it along at 70 or so, and at the next major stop, it was uncoupled from its own record-breaking train. The engine that took over was an older machine of an earlier generation, unstreamlined, unremarkable, and entirely capable of finishing the job. The fastest locomotive in the world limped away to a workshop, while a slower one finished its journey for it. The railway's publicity department, it turned out, had planned for this. They had already prepared photographs and were handing them to the press before the replacement engine had even fully arrived. The record went around the world. The melted bearing did not. And here's the thing people get wrong. that failure was not a scandal, and it was not an accident. It was a price. It was a bill presented in metal for asking a machine to work at a speed nobody had ever asked before. The locomotive was repaired and backhauling trains within days. It went on to run for another quarter of a century and covered something close to 1.5 million miles before it retired. So it was not destroyed, but it did tear something inside itself apart to get there, and it never went that fast again. That is the real ceiling of steam. Not boiler pressure, not horsepower, not even the courage of the crew. It is the simple, unforgiving physics of heavy metal parts being violently reversed thousands of times a minute in a mechanism that must be lubricated by oil while being shaken hard enough to throw that oil away. Engineers spent the following years trying to beat it, and their attempts tell you how serious the problem was. Some split the drive between two sets of smaller, lighter cylinders and rods so that no single piston assembly had to be so heavy. Some designed rods and pistons from lighter alloys. Others gave up on the reciprocating engine entirely and tried to drive the wheels with turbines instead, chasing smooth rotation instead of a punch. Nearly all of these machines were fascinating. Almost none of them were successful enough to matter because they were solving a problem for a technology that was already being quietly replaced by something with no reciprocating masses at all. The engine that killed steam was not faster. Early diesel and electric locomotives were often less powerful at speed than the best steam machines of the same era. What they had was an enormous, boring advantage. They could run all day without shaking themselves loose. Their traction motors simply turned. There was no piston to stop and reverse, no hammer blow to pound the track, no bearing hidden between the frames that you could only reach by crawling into a pit under a hot engine with a lamp and a mirror. Steam lost the race. Not because it was slow, but because going fast cost it too much. There is one more reason the record still stands, and it is the least romantic reason of all. Nobody is allowed to try. The surviving fast steam locomotives in the world are heritage machines, priceless, irreplaceable, and operated under speed limits far below what they were designed for. The tracks they run on are shared with modern services on modern schedules. The one machine that could plausibly make the attempt is not permitted to, and the museum that owns the record holder has no intention of risking it. Which means a number set in the summer of 1938 by a 4-month-old engine that melted a bearing achieving it is likely to stand forever. Not because the technology could go no further, but because the world stopped asking it to. The next time you see a preserved steam locomotive drift past on an excursion, moving at a stately 40 miles an hour with a crowd photographing it, look at the rods. Watch the way they rise and fall and reverse over and over with a rhythm slow enough to follow with your eyes. It looks almost gentle. It looks like something you could reach out and touch. Then imagine that same motion happening 3 times faster than your eye can track, with the forces multiplied 4-fold, in a machine wrapped in blue steel and screaming down a slope in Lincolnshire with a paper roll recording every second of it. And remember that on the one day a machine like that went as fast as steam has ever gone, it came back smelling of aniseed. That was the machine telling its crew the truth that every engineer already suspected, that they had finally found the edge, and that the edge was made of metal and it was melting.